because you cannot stick conductivity into Hamilton's principle. It's a conservative principle. You can only kind of paste it on with what was later called the Rayleigh dissipation function. But it's bad because energy is lost from the system. This again is the Achilles heel of Maxwell's theory. But it seems to work pretty well. And Maxwellians were very happy to say that, listen, we really don't know what's going on with conductivity. Let's just leave it to the side and see as far as we can get. The assumption being that you could somehow manipulate, even with dissipation, the field equations to get around this problem. Now, shortly thereafter, 1879, a new experimental novelty is discovered at Harvard by, well, it was actually discovered at Johns Hopkins by John Henry Hall, who was the student of Henry Rowland. And Rowland had founded the physics department at Johns Hopkins, which was the first PhD granting such department in the United States. It was founded by Henry Rowland. Rowland had knew Maxwell's treatise, studied it carefully, and he had also worked in Berlin under the great Hermann von Helmholtz, who was deeply involved in electrodynamics at the time. Well, the experiments began, and he had a notion that if you put, say, a plate of copper in a strong magnetic field, make it orthogonal to the surface, that the current lines in the plate would be altered. Now, this is not microphysical. It's no notion that there are particles